multimodal
We
neural
need to
network.
record. Okay, thank you.
So sorry.
No, I'm sorry. Could you start introducing yourself again? We just hit record. Thank you. I'm sorry.
Of course. Hi, I'm Aanchal Poddar. I'm a senior at Amity Regional High School. My mentor this year was Professor Shayla Nabawi, and my project was developing a multimodal neural network for the object detection and captioning of chest X-rays. So first, a quick table of contents of my presentation. We will start with an introduction of why I pursued this specific topic, and then we will go over the literature review, in which I explain some previous research and how it's influenced the experimental design. Next, we'll go over the experimental design, which is essentially the methodology of the project, and then we have the results and the results of the project thus far, and lastly, we will go over the results and a discussion of my future work. So first, an introduction. My motivation behind this project is the lack of accessibility within the healthcare system, which has been highlighted recently by COVID-19, but also been a general constant throughout the years. My main concern lies with the time and effort needed to train radiologists, and because of this, the low accessibility to X-ray-based diagnoses. Many researchers have used deep learning-based approaches to solve this problem, but they tend to be a black box without any explanation for the outcome, which makes results hard to verify and raises concerns about whether or not the model is focused on the correct regions of concern. So my goal of this project is to help fix this by investigating different methods of increasing the interpretability of diagnostic predictions made by machine learning algorithms. So now my literature review. And first we'll go over the bounding boxes, which is the first method I investigated. And bounding boxes are essentially a rectangle surrounding a relevant object, in this case, surrounding an abnormality within a chest X-ray. And this provides both the class of the abnormality and also the location within the image. There have been deep learning approaches to creating bounding boxes, which generally involve finding some data set with chest X-rays, diagnoses, and a coordinate for the bounding box, and then next training some variation of a convolutional neural network to predict the coordinates. One major issue with doing generating bounding boxes for chest X-rays is that it's very hard to find a data set, as creating a data set involves the manual annotation of bounding boxes on the image. However, there has been previous research made for more general images, such as the one shown on the top right, which has more daily use objects such as cars, people, etc. And these models tend to have very high success. One of such models is the YOLO v5, which is an object detection model made again for daily objects. And to utilize the success of such previous models, we will be using transfer learning, which is retraining a model made for one purpose to suit another similar but different purpose. And this is useful in problems with little data like the one we have today, due to the fact that the model can essentially share knowledge from the previous problem to this one, meaning they don't have to learn from the ground up. Another reason we'll be using YOLO v5 for this specific project is because YOLO v5 is a flexible model and can easily be retrained to suit another problem. And next we'll go over the chest X-ray captioning, which is the second method of making diagnoses more interpretable that we looked over. And image captioning is essentially just the generation of some natural language to describe a certain image, as shown in the lower left. They're captions for general images. And this obviously has many uses outside of the medical field, as it provides a more detailed, thorough, and natural analysis of a picture. However, it also has the downside of the complexities of human grammar, since it's very hard to emulate human grammar using a machine. So, of course, this has been researched in the past, but there has been less focus on medical images and generating medical text reports due to the complex vocabulary and concepts that come with the field. That being said, we can apply previous ideas from the general images to the specific topic. And in previous research, there have been three main categories that have been researched. The first one is template-based techniques, which essentially detects an object in a picture and then uses templates, pre-made templates, in combination with human grammar rules to create a text report. And this has the downside of being very inflexible, as it is only working with a template and isn't generating language from scratch. The second technique is a retrieval-based technique, which retrieves images similar to the sample and combines or reuses the captions. This will most likely be very coherent, but is limited by the sample size of the images that it can retrieve. If it doesn't have enough images to compare to the sample, it won't generate a good caption. And lastly, a deep learning-based technique, which is the one we looked at here. And this mostly depends on some form of a decoder-encoder network and also CNNs to extract and put together relevant information. The entire process is done by a deep learning model, and humans have little involvement in the process. And now some experimental design and methodology of the project. For bounding boxes, we use the NIH chest X-ray dataset, which has 100,000 or 112,000 images with disease labels from over 30,000 unique patients. And specifically, we used a subsection of this dataset, which had 880 samples, as this subsection included the bounding box coordinates, unlike the rest of the dataset. These 880 samples had 8 disease labels, which are listed here. And these images also required some pre-processing before being fed to a neural network. These pre-processing steps included applying a Clawey filter, which increases the contrast as shown on the bottom right. Also resampling, which is essentially using data augmentation to perform various flips and rotations on the image to increase the number of occurrences for each image, so that way we could have more data to work with. We also had to scale pixel values and scaling the image size to make the image interpretable to the machine. And this is just a general framework for the algorithm. It's essentially just the data cleaning, which we outlined in the last slide. Next, we have to train the model, which is fine-tuning the YOLOv5 model I discussed earlier to the National Institute of Health's chest X-ray dataset. And lastly, some evaluation metrics, which we will discuss in the results section. For the image captioning problem, we used the MimicCXR dataset, which is a set of 377,000 images published by MIT, which are each paired with a text report. As you can see in this image here, which is a sample from MimicCXR, occasionally you'll have multiple images associated with one text report. In our case, due to storage limitations, we only used 500 samples. And this also requires pre-processing both on the images and on the text reports. On the text reports, we had punctuation and stop removal, which is stop word removal, stop words being words like the, is, and, words that don't contain any relevant information. We also did stemming and adding start of sentence and end of sentence tokens for the machine to know where the sentence starts and ends. And on the images, we also applied the same image pre-processing techniques as the bounding box model. So the framework for this algorithm is a bit more complicated. It's outlined here, and I'll verbally describe it to you, of course. Essentially, we're going to have some kind of caption generator, which has 2 inputs, a set of labels and a visual feature, and both of these are extracted from the image. The visual feature that's extracted from the image is extracted by using some kind of neural network, and then this is fed to the caption generator. And then we also have a labeling algorithm or labeling classifier, which extracts a set of 10 keywords from the image and then is sent to the caption generator. These 10 keywords are chosen from a vocabulary, which we have chosen by taking the top 100 most frequent words from the set of medical reports, obviously excluding any words that don't have any relevant medical information. As of now, research has not been completed and the caption generator has not been finished due to processing limitations. So now the results of the work thus far. So the bounding box model, on the right, we have the architecture of the model, which we had to retrain. On the top left, we also have a confusion matrix of the classification results. The darker blue classes are the ones that were more often correctly classified. Those include cardiomyopathy, pneumonia, and atelectasis. And on the bottom here, we have an explanation and comparison of various IOU scores from our model and comparing it to other researchers' models. And an IOU score is essentially a way of explaining how well the bounding boxes were generated, how accurate they are. And this is calculated by dividing the area of overlap between the ground truth and the predicted bounding boxes, taking that and dividing it by the area of union, or the union of the 2 bounding boxes. As you can see here, Rosenberg et al., which uses a ResNet-based approach, had the highest general IOU scores, and ours came generally in second, followed by Lee et al.'s work. For the captioning model, again, research has not been completed, so we don't have any definitive results. However, we can explain how well our label classifier has done, since other people have also made label classifiers for similar projects. A ResNet-based model has done the best with a 0.501 score. F1 score, and an F1 score is essentially a more rounded version of accuracy, as it takes into account the true positive, false positive, and true negative and false negative rates. Our model did the second worst, and we'll explain most likely why in the discussion section, and the image semantics and the CNN groom-based models did decently, but could have done better. And then lower here, the bottom here, we have the architecture of the visual feature extractor. This is mostly based in the VGG16 neural network. It's based off of that, as that network has done well in the past. So now some discussion about our results.
2 minutes.
Thank you. So for our bounding box algorithm, the atelectasis, cardiomyopathy, and pneumonia generally saw high results, and this is most likely because they're very easy to detect. Pneumonia generally causes some kind of blurriness in the chest X-ray. Cardiomyopathy, which is an enlarged heart, is obviously very easy to detect. However, infiltration, mass, and nodules were not as often classified correctly, and this suggests a need to investigate exactly why this happens. Specifically, it might be because they're very easy to mix up with other diseases, or maybe they're very similar to another disease. Other work has also seen success by increasing the amount of data they had to work with by combining different data sets. So we will most likely also pursue doing that in the future. So again, for the captioning analysis, results thus far are inconclusive, and our labeling algorithm does show some promise as there is room for it to grow. But this growth would most likely only happen if we diversify the vocabulary by using more samples. And other researchers also improve their vocabulary by dividing it based on medical semantics, meaning they had different categories based on if the words had to do with specifically thoracic diseases or pulmonary diseases, whichever ones they were related to. And now we'll talk about some limitations of my project. The first thing being the most important one, that our model's performance is only going to work, the model will only work as well as the images it's given. If the image quality of the image that the model is given is low, then the model will also not perform very well. So it is important that the image quality is high. Next is the processing power. As I said before, we weren't able to use a lot of data for the captioning model because the data did not work. There was not enough storage to load all the data. So that means that our model also did not perform as well. And lastly, I don't have a very good knowledge of medical terminology, meaning that there might be some complexities that I'm not understanding. And this could only be, sorry?
Yeah,
That's a hard stop at 12 minutes. Thank you so much for your presentation. Connie, have you stopped the recording?